This is problem 39 from chapter 15. In problem 39, we have a ballistic pendulum which consists of a 4-kilogram wooden block originally at rest, and the angle theta is equal to 0. When a 2-gram bullet strikes and becomes embedded in this block, it is observed that the block swings upward to a maximum angle of 6 degrees. We are going to estimate the initial speed of the bullet. For this problem, once again, we're going to use both the work energy and the impulse momentum conservation law. For the collision itself, we will use the impulse momentum conservation law. And since we are only going to estimate the initial velocity of the bullet, we're going to assume that the bullet becomes embedded in the block before the block begins to move upwards. So we're just going to look in the horizontal direction. And initially, the block is at rest. So the momentum that we have is just coming from the bullet, which is 2 grams. So the initial momentum is the mass of the bullet times the initial velocity of the bullet. If our system is just the bullet and the block, and we're assuming that the bullet comes to rest in the block before the block begins to move upwards, then there are no forces acting in the horizontal direction because the rope is hanging straight downwards then. So the only forces we have are the forces in the rope and the force of gravity, which are all in the vertical direction. So the impulse in the horizontal direction is equal to 0. So the initial momentum must then be equal to the final momentum. Afterwards, the bullet and the block are going to move together, and we're only going to look immediately after when the block is moving in the horizontal direction. This is 4.002 times the velocity of the bullet and the block together. So these two are equal to each other because the impulse is equal to 0. So we have I want the initial velocity of the bullet, but I don't know the velocity that the bullet and the block have right after the bullet strikes the block. So now I'm going to use the work energy conservation law. I know the maximum angle here. And at the maximum angle, the bullet and the block would have a velocity of 0. So the kinetic energy is 0 when you're at the maximum angle. The only forces that you have acting on the system of the bullet and the block as they're moving upward together would be the force of gravity acting downwards and the forces in the rope. But the forces in the rope are going to be perpendicular to the direction of motion, just like the normal force is perpendicular to the direction of motion for an object which is sliding on a surface. So these forces in the rope do no work. The only force that does work is the force of gravity, but we can use gravitational potential energy for that. So let's say the gravitational potential energy is 0 initially when the bullet strikes the block. So we have our kinetic energy plus our gravitational potential energy plus the work done by forces other than gravity, which is 0, is equal to the final kinetic energy, but this is 0 because when you're at a maximum angle, that would be the turning point where the velocity is 0, plus the final gravitational potential energy. But we're saying the initial gravitational potential energy is 0, so we have initial kinetic energy is equal to final gravitational potential energy. This kinetic energy that we're using is after the collision, so that would be what we have, the velocity that we have here. So this is 1/2 the mass of 4.002, that's for the bullet and the block together, times our velocity squared for the kinetic energy is equal to the mass of the system times g times the height. I can figure out the height because I'm given the length of the rope here, and I know the angle is 6 degrees. So the height that I have, if I say the initial gravitational potential energy is 0, the height that I want is the difference that I have here. The rope's staying the same length, so from here to here is also 1.25 meters. So I want the difference that I have here. That would be 125 minus the vertical component of what I have here, which would be the cosine component of 1.25. So this height is equal to 1.25 meters minus 1.25 times cosine of 6 degrees. Then we can solve for the velocity, which I'm going to do very quickly, but you can check this on your own. You have the 4.02 on both sides, so that cancels out. You have the 1/2, which you have to bring over to the other side, so that would be a 2. And then you have 9.81. You can pull the 1.25 outside, and you have 1 minus cosine of 6 degrees. And that gives you 0.366 meters per second. But this is not what we were looking for. We were looking for the initial velocity of the bullet, which I can get by using the equation that I have up here. So the velocity of the bullet is equal to 4.002 divided by 0.002 times 0.366 meters per second. And that gives us 733 meters per second for our estimate of the initial velocity of the bullet. And that concludes problem 39.